Next, I'll show you how to use the SISOTOOL in MATLAB to find the step response. So let's say we have a system where the system has a pre-filter F, and then you have a compensator C, you have a plan G, and you have a feedback H in these configurations. In this case, let's define F equals to H equals to 1. So for C equals to 1, the compensator equals to 1, meaning that it's a pure gain. Let's say your system G2 is equal to 6 over S squared plus 3.6S plus 6. You can the open loop transfer function is equals to C multiplied by G multiplied by H. So C equals to H equals to 1. So your open loop transfer function is equals to G2. And for the closed loop transfer function, you can find the formula. You can use the formula G over 1 plus GH. So you can finally find the closed loop transfer function of the system is 6 over S squared plus 3.6S plus 12. So let's use the SISOTOOLs. So let's define the transfer function as show you before. This is the transfer function. So let's define this. Okay, so to call the SISOTOOL, you can use the SISOTOOL function, and you put the system G2 into the SISOTOOL function and you run it. Okay, so you'll see this window here where we use the first architecture here, so FCGH, and let's see the control architecture. So you have FCGH, your input is specified as R, output is Y. Okay, and we want to see the step response. So for the closed loop transfer function, so tick on here. So you want to see the closed loop response, Y to R. So this is the response. So this is for your compensator or proportional controller C equals to 1. So what happened when let's see for the open loop system here. Yeah, this is the open loop system, yellow, and the blue is the closed loop system. Let's see the plan G. So the plan G here is equals to the open loop transfer function, like I mentioned before. So the plan G is equals to the open loop transfer function, and the closed loop transfer function is slightly different as depicted by this blue, solid blue lines. So let's change the compensator to 2. So let's see here, when we enter compensator equals to 2, then it changed. You see here, all three, the open loop transfer function and the closed loop transfer function is different, but for the plan remain the same. G2 remain the same as G2, however you change the compensator value. So let's see what happened actually. So when you set the compensator C equals to 2, what happened to the open loop transfer function? You have C multiplied by G multiplied by H. H is equals to 1. C now is equals to 2. So you have 12 over S squared plus 3.6 S plus 6. So now the open loop transfer function for the system is not the same as the plant anymore. And for the closed loop transfer function, you have CG over 1 plus CG. So you have this, and you can simplify it into 12 over S squared plus 3.6 S plus 18. So that's why you see the open loop transfer function plot and closed loop transfer function plot change with the changes in C value. So basically, when you find the characteristic equation when the C is equals to 1, you have these two roots, or you have these two poles at this location, 1.8 plus minus J 2.96. And when you change the C equals to 2, and you find the characteristic equation and you find the roots of the denominator, you find that it will result in different poles at 1.8 plus minus J 3.84. So you just change the gain or the compensator C. What happens is that you change the closed loop transfer function, and indirectly you change the poles locations. Okay, so we will cover about these phenomena in details in the next lecture in root locus. So for the time being, let's see here. So again, so I just untick the open loop and the plant G here. So I just want to show you what happened when we increase the compensator value to 3, 4, 5. So from here, basically you just can click on the plot, and right click, you can see the characteristic. For example, when we want to see the peak response, you just click on peak response and click on the dot here. It will give you the value of overshoots in percentage, the time it happened, in this case 0.537 seconds, and the amplitude of the peak response at 1.14. So in real time, if you change again to 4, it gives you the results. So you can try to play with this SISOTOOL, and you see what happened to the step response, what happened, even you can change to impulse response, and you see the characteristic peak response, settling time, and you can see what is the value by clicking on the dot. So I hope you can try to play with these SISOTOOLs, and also you can play with MATLAB to enhance your understanding of the time response topics that we have learned in the lecture.